Hi everyone, I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the double slit diffraction, that is Fraunhofer diffraction due to double slit. So at the end of this lecture, students will able to understand the conditions of maxima and minima. They can also understand the distribution of intensity due to the Fraunhofer diffraction due to double slit. See, this is the double slit diffraction due to Fraunhofer diffraction. Here we are considering two rectangular slits A1 B1 and A2 B2. These two are the rectangular slits whose lengths are perpendicular to the plane of the board or the paper, and from the sideway the light rays are entering the slits. The width of the slit, each one is small a is the width of the slit, and the separation of the slits is E, from first light ray to first light ray or center to center, whatever it may be, the separation of the slits is small e. Here from sideway the light rays are entering. Generally the diffraction means bending of light rays. Bending of light rays into the geometrical shadow of an obstacle. Here the light rays are entering the slit and they are bending. Here the angle of deviation is theta. Each one can be considered as a single slit, and later we combine these two effects. Suppose consider A1 B1 is the single slit and the light rays are passing through that one. There is a bending of light. Actually, in case of Fraunhofer diffraction due to single slit, the resultant amplitude is given by A theta, or the resultant intensity is given by I theta or I1. Here similarly consider the second slit. At the second slit, here also there is a bending of light rays, and the resultant amplitude is given by A theta, and here the intensity is given by I2, previously it was I1 say. Anyhow, this is one diffraction pattern due to single slit, this is another diffraction pattern due to single slit. The two diffraction patterns will superimpose and finally they will produce one pattern, that what we are going to discuss now. Indirectly we can say one thing, interference of the diffraction patterns will give us final diffraction pattern. You may call it as diffraction or diffraction, no problem. The two interfering, the two diffracted waves are superimposing and interfering, finally they will produce one diffraction pattern. So that what we are going to discuss now. Actually, in case of the double slit, what is the resultant deviation? It is given by theta. So generally we have one formula, the phase difference is equal to 2 pi by lambda into path difference. How much path difference is there? Suppose you consider first light ray to first light ray, the separation is given by E, or center to center it is E. The angle of deviation is theta. Then what is this path difference? Path difference, you can take sin theta is equal to opposite by this what do you say, that B1 A2, automatically A1 A2, automatically you will get, that is say E, A1 A2 it is E. Therefore what is that sin theta means path difference, the path difference is equal to E sin theta, that is the path difference. Therefore what is the phase difference? Already we have some idea, the phase difference is equal to 2 pi by lambda into path difference, that is E sin theta. So anyhow, this is the resultant phase difference. Actually according to superposition principle, what is the resultant amplitude? If the two amplitudes A1 and A2, two amplitudes or two waves superimposed on each other, what is the resultant amplitude? The resultant amplitude R is equal to root over A1 square plus A2 square plus 2 A1 A2 cos theta or cos phi. That phi is the resultant phase difference. Here So R is equal to, we eliminate this root. Instead of A1 and A2, we have A theta and A theta. Already we have seen A theta, it is due to the single slit diffraction, the resultant amplitude. This is A theta, that is also the resultant amplitude. Instead of A1 and A2, we have A theta, A theta. That is why, what is the resultant amplitude square? A theta square plus A theta square plus 2 A theta cos delta. So substituting the same thing, we get, so this kind of 2 A theta square, it is taken out common. So 1 plus cos delta. What is 1 plus cos delta? 2 cos square delta by 2. So therefore 2 into 2, you will get 4 A theta square cos square delta by 2. Now what is this A theta square or intensity? Actually intensity I is equal to A theta square mod A theta square we write. Actually in case of single slit diffraction, already we have one notation, that is the resultant intensity I naught sin square beta by beta square. We are taking from the single slit diffraction, Fraunhofer diffraction due to single slit intensity. That's why you will get I theta is equal to 4 I naught sin square beta by beta square into cos square delta by 2. Here actually two terms are there, I naught sin square beta by beta square and cos square delta by 2. 4 I naught cos square delta by 2. This is actually the diffraction term and this is the interference term. Two terms are there, interference term is there and also the diffraction term. Both the terms we have to analyze. What are the interference maxima? What are the diffraction maxima? What are the interference minima? What are the diffraction minima? That what we have to determine here. Already in case of single slit analysis, same way we analyze sin square beta by beta square. So adopting or we just taking the conditions from the single slit diffraction Fraunhofer case. So what is the condition for maxima? What is the condition for minima? Already say beta is equal to plus or minus m pi. That is the case of the minima. That's why pi, 2 pi, 3 pi, these are the minima cases. In the same way, in case of the interference, what are the minima? That means this cos delta by 2 must be equal to 0 or delta by 2, cos delta by 2, it is equal to 2n plus 1, delta by 2, it is equal to 2n plus 1, pi by 2 we get. Therefore, that delta is equal to 2n plus 1 we get, where n is equal to 0, 1 to 3 you take. So we will get phi is equal to pi, 3 pi, 5 pi, odd values. At the values of delta is equal to pi, 3 pi, 5 pi, interference minima we get. At the values of beta is equal to pi, 2 pi, 3 pi, etc., diffraction minima we get. These are the conditions of minima in case of interference and diffraction. Similarly, what are the maxima? Suppose you observe the maximum intensity cos square delta by 2 or cos delta by 2, it is equal to plus or minus 1. When we get this one, where delta by 2, it is equal to n pi or m pi. That's why delta is equal to 2n pi. At these values, we get the maxima. That's why delta is equal to 0, 2 pi, 4 pi. Even values of pi, we get the maxima. And similarly, what is this delta? Actually we have taken that delta is equal to E sin theta. Therefore, this E sin theta is equal to, or observe this one, delta is equal to 2 pi by lambda E sin theta. Same thing I am taking, substituting here, we get E sin theta is equal to 0, lambda, 2 lambda, 3 lambda. At these values, we get the interference maximum. Already interference minima, diffraction minima, already we got. Now these are the conditions for interference maxima. Already in diffraction maxima cases, in case of single slit we can adopt. That is, at the values of beta is equal to, what we get in case of diffraction, sin beta by beta must be maximum, or that is equal to 1, or sin beta is equal to 1. Beta values already we know. Say on simplifying, in case of single slit diffraction, we get at the values of beta is equal to 2n plus 1 lambda by 2, or sorry, that pi by 2 we get. Therefore, plotting the graphs, we got the maxima points, minima points in case of interference and also diffraction. Observe, this is the graph for interference. So, the maxima and minima positions, angle is taken on the x-axis, intensity is taken on the y-axis. Then we get the maxima and minima at different points. Similarly, sin square beta by beta square, that those values are taken on the y-axis, and corresponding lambda values are taken, or pi values are taken on the x-axis in case of diffraction single slit. So, already we got center, this is the central maximum, first minimum, first maximum, all these things we are taking directly from the single slit diffraction. Combine, this is the graph for interference, this is the graph for diffraction. Then combine these two. Actually, there is one case, one condition we can say, when maxima and maxima superimpose, we get maxima. Interference maximum and diffraction maximum superimpose, we get maximum. And minimum superimpose, minimum is darkness. When the minimum of interference, minimum of diffraction superimpose, we get minimum only, darkness only in the resultant graph I am talking. So, when the maximum and minimum superimpose, what happens? A little bit maximum we observe. Here actually the diffraction is the dominating term. If the diffraction maximum, interference minimum superimpose, we get somewhat maximum. When the minimum of diffraction, maximum of interference superimpose, little bit maximum we find. Anyhow, diffraction is the dominating term in this one. When you observe this graph, on either side of the central maximum, we observe two peaks, and we get some minimum. Again, one more, this is actually called central spectrum. K is equal to 0, central spectrum. Suppose you take the double slit, on either side of the central maximum, you will get two peaks, right side two peaks, left side two peaks you will get. Again, you go somewhere, some long distance, there also on either side of the central maximum, you will get left side two peaks, right side two peaks. That is called first order spectrum. So, that is called first order spectrum. Similarly, you go to somewhat distance, there also on either side of the central maximum, you will get the two peaks, left side two peaks, right side two peaks. That is called second order spectrum. That means K is equal to 0, central spectrum, first order spectrum, second order. Similarly, you go to the left side, first order, second order, several spectra we get. To understand this one, if you take the n slits case, that is nothing but grating, we can understand completely about this one. Here we are just combining the interference graph and the diffraction graph, these two superimpose, finally we get the resultant intensity. So, actually what I just started is, this is the double slit diagram, two slits, two parallel rectangular slits are taken, and those lengths are perpendicular to the plane of the paper. From the side where the light rays are entering, and they are bending because of the diffraction. So, and at each and every slit there is an there is a diffraction pattern. These two diffracted waves are superimposing and interfering. Finally, again we get the diffraction pattern. That what we have analyzed here. So, anyhow, in this topic, what we observed is the double slit diffraction, Fraunhofer diffraction due to double slit we have discussed, and the diagram, ray diagram, and corresponding conditions we have seen, and afterwards we have discussed the intensity distribution, how the intensity of light is distributed, or what kind of peaks we observe in case of double slit we have discussed. Okay, that's it. Thank you.